Hi, my name's Andy Zimmerman. I'm the Chief Technology Officer here at Grace Technologies. Today, I want to walk through kind of a high-level overview of ways in which 24/7 industrial Internet of Things-based vibration monitoring technologies can be used in a real practical way to reduce downtime in the industrial facility. So, I'm going to make, before I start this, a couple of assumptions. First and foremost, I'm going to assume that everybody interested in this presentation believes that vibration data could help you maintain, in a better way, the critical assets that are located within your facility. So I'm going to assume that either that is true or that you know that vibration data can help you maintain your critical assets because you're actively doing it. And you're coming to this presentation because you're looking for a way to augment your existing vibration analysis techniques with a more frequent inspection that likely is done using the IoT-based technologies that are coming to the table in recent years. So while these two things aren't mutually exclusive, I do think that the target of my presentation here is really for both of these groups. Either you haven't played with vibration before and you're interested in learning what it can do for you, or you have played with vibration before, you know how powerful it is, and you're looking for a 24/7, always-on kind of technology. So to kind of refine what I'm going to be talking about a little bit more, this talk is going to be twofold. First and foremost, I'm going to give a very basic introduction to what vibration monitoring is, with a real solid focus on rotating equipment. So there's some stuff that's going to be out of scope of what I'm going to talk about today. And then I'm going to move on and talk about, from an IoT perspective, an overview of how those Internet of Things-based technologies can be used to provide value through always-on or 24/7 vibration monitoring. Now, this talk is not a comprehensive course in vibration monitoring. That can take hours, most of the time days, to actually get through all of that content in full detail. And I'm definitely not going to talk about any sort of complex or non-rotating based vibration applications. They just create too much complexity, too many edge cases to really cover in an effective way in a short presentation like this. So why are we at Grace Technologies presenting on this topic? Well, Grace has come at the industrial Internet of Things space from a real core industrial focus. If you don't know Grace, we were founded back in 1991 by Phil Allen. He's pictured here. We just recently entered a second generation of family-owned business leadership as Phil's son Drew took over as our CEO. We've been, over the course of that 30 years, most of that time has been spent as a Rockwell Automation Encompass partner, which has really positioned us well to understand the industrial automation world and has allowed us to thrive as an industry leader in technologies that are driven by electrical safety needs. So why am I here? I actually come to this talk from a really kind of strange perspective. My background actually isn't in the industrial space. It comes from developing technologies that were designed to take data from vibrating systems in the structural space and make assessments about the health of those structural systems. So the technology that we're talking about here was really developed with funds coming from a variety of different sources, from the Department of Defense, the National Science Foundation, the Department of Homeland Security, the U.S. Department of Transportation in collaboration with Union Pacific, and just a variety of other funding sources that had interest in developing predictive or condition monitoring technologies that would allow for early indication of degradation in a variety of different systems. So we've deployed this technology on a ton of different engineered assets, from long-span bridges to wind turbines to burning or damaged structures after, say, a terrorist attack or an earthquake. And then most recently, we've transitioned that technology into the industrial space to really look at ways in which it can detect at an early stage the onset of damage that might lead to downtime in an industrial facility. So at a high level, I'm going to cover four things in today's presentation. We'll talk about why vibration monitoring is important. We'll then get into the nitty-gritty of the basics of what vibration is and talk about how vibration monitoring works in practice. And then I'll close by talking about kind of the IoT portion of that and how we can deploy always-on technologies to monitor vibration in the industrial setting. So we'll start just with the overarching vibration monitoring value proposition. So really there's three main reasons, in my view, of why you'd want to monitor equipment using industrial Internet of Things technologies. The primary reason is to reduce unscheduled downtime. That's probably why everybody's interested in this, right? If we can detect failures early on, we can actually schedule out maintenance activities and avoid unscheduled downtime. And that unscheduled downtime can lead to incredible expenses, pretty much across industries, when a facility's down in an unexpected way. The second thing that monitoring equipment with industrial Internet of Things technologies can do is to reduce maintenance expenses, right? If we're detecting damage in systems early, we can reduce the severity of the issues that are occurring and possibly eliminate the need for replacement, and as such, reduce the cost of repair. And then the last kind of piece of the puzzle here that we at Grace are really passionate about is actually by deploying these sorts of technologies, we can increase worker safety. It's kind of known that 70% of workplace accidents, that's a huge number, occur during reactive maintenance activities. So the idea is that if we can reduce downtime and eliminate the need to be running around putting out fires in a reactive way, we can actually substantially reduce the onset of workplace accidents, and as a whole make a safer workplace for industrial workers. So inside that ecosystem of IoT technologies, why do we focus so much on vibration? Why is vibration the big topic that we discuss? And really it boils down to vibration lets us get an earlier indication of failures within our industrial assets. So I like to talk about this in the context of this PF curve that you're seeing here. So this transitioning from potential failure to functional failure. And this graph, if you look at it kind of on a y-axis perspective, it's telling you how resistant a system is to failure. So as this blue line goes down, it's getting less and less resistant to the eventual failure of that asset. And then on the x-axis, obviously, is time. So that's, as you move to the right, we're going further and further in time. The idea here is I can wait till the very end of this spectrum, and I can just wait till the thing catches on fire or stops working. That's one way to maintain an asset, right? But most of the time, we're doing something better than that. We're moving up this curve. We're waiting for a human to detect, at least a human to detect the onset of this failure. You usually hear something rattling, or there's an increase, you touch it and it's really hot, that sort of thing. This is the human level of detection where we hear or we see something wrong with the asset. Now, before that, we can actually see things like temperature increases or increases in current consumption of that asset. These are early indications that something's going wrong. There's a lot of value in just monitoring the current and the temperature draw, the current draw and the temperature of any asset in an industrial facility. But if we really want to get at early stage detection, we need to start looking at other technologies. And in this case, in the context of this presentation, we're going to talk about vibration, because that usually occurs before you see any current increase or rise in temperature, right? This is low frequency vibration, things that we typically deem under the ultrasonic level. I'll talk about that later. And then if we want to get even earlier indication, we actually can look at high frequency vibration, which gets us at kind of those early micro cracking or early stage failures in a rotating asset. And then the last piece of this puzzle, and I'm not going to touch on this at all today, would be to take data that's being captured and actually do a predictive analysis and detect the probability of a degradation based on data that may not have even become clear in that ultrasonic or high frequency spectrum. So the last piece of this puzzle that I want to point out, this green line that's been plotted at the bottom of the screen, the closer you get to failure, the more expensive that asset's going to be to repair. And this decouples it completely from even the downtime that's associated with not knowing in advance, right? So all of these things together lead to the importance of monitoring vibration in the industrial setting, right? We get a reduction in downtime, a reduction in the cost of repair, and like I said in the last slide, you get a safer environment for doing maintenance. So what can we do with vibration data? Well, there's a lot of things, but we're going to focus here on the ability to detect, trend, and classify long-term degradation. Things like misalignment or unbalance or looseness. Also things like issues with a bearing that may indicate the need for a replacement of that bearing, or there's a kind of a subset of problems that can come up anytime you have a gearbox involved. So these are things that we're talking about doing with vibration data. And we can apply that to rotating equipment, things like motors or pumps, fans, compressors, anything that spins in a regular fashion. So we can do a lot of other things, and most of these things are kind of out of the scope of today's discussion, but I wanted to bring them up. We can detect, trend, and classify degradation, things like cracking or material softening or hardening, loose footing of equipment, in structural systems like cranes, footings, etc. These sorts of cracks can occur and be detected using vibration. This is a slightly different scenario than the rotating equipment one, and I'm going to not touch on these today, but we can also deploy vibration technologies to monitor things like presses or AGVs, where they're subjected to impulse loadings or impact loadings. But again, all of these things kind of outside of the scope of what I want to talk about today. So what can't we do with vibration, or at least in the discussion that we're talking about today? We find it hard in general to use low frequency vibration to monitor equipment that is running at really low speeds. One example I ran into recently would be a low speed screw conveyor. Also, lubrication applications typically require, just like those low-speed RPM type applications, ultrasonic information coming from a high-frequency vibration sensor or a dedicated ultrasonic sensor. The one big thing that we can't do in the context of this talk is high-speed machine protection. So if I've got a motor or a fan and somebody throws a wrench in there, the type of vibration analysis we're talking about today is really designed to detect the onset and then the increase in degradation associated with a failure that's occurring slowly over time, not designed to detect a rapid failure caused by some outside event. So I've talked about a lot of this, but I'm also not talking about non-continuous rotating equipment here today. There's some complexities that come from a piece of equipment that's only on for 10 minutes a day or something like that. Makes it difficult to deploy IoT technologies on. Not that it can't be done, but outside of the scope here. Rotating equipment with an unknown shaft speed. So, for example, if you have a variable speed drive that doesn't have a tachometer associated, we have no way of knowing the speed of the shaft. That can get very difficult to do the type of monitoring that we're talking about today. I already mentioned structural systems and then any impulse or impact loading scenarios. So that just sets the stage for what we're talking about. There's a lot of kind of out of scope questions that I'd love to address offline. So with that kind of value proposition in mind, I'm going to dive into the basics. And this is really the basics of vibration. In the context of rotating equipment, which is really what we're focused on here today, everything we do really starts with the shaft. It rotates like you see here, and if everything's healthy, that pillow block bearing that it's running through shouldn't move at all. That shaft is spinning in a really nice, smooth fashion, and there's really no vibration to be seen in the idealized healthy scenario, right? But if we introduce a defect to this particular equation, we start to see vibration. That pillow block is going to start to displace vertically, in this case, and we can measure that as a displacement. That's going to displace in terms of inches. And that change in displacement is going to yield a velocity. So it's moving with a certain speed in this case, right? We can monitor that in terms of its inch per second movement velocity-wise. We can also look at the change in velocity, and that gets us to acceleration, which is usually monitored in either inches per second squared or in units of g, right? That's the gravitational acceleration. So to kind of summarize, vibration can be conveyed as either the displacement, the velocity, or the acceleration experienced by the asset that we're monitoring. So how do we monitor that vibration? Well, there's a lot of different ways. If we wanted to get at the absolute displacement of that pillow block bearing, we would have to deploy something like a potentiometer, a linear voltage displacement transducer. There's a lot of non-contact optical options here. The problem with monitoring displacement directly is it requires a stable reference point. So if this thing's monitoring, I have to actually have some stable reference point to measure that against. And that's hard to find in an industrial setting. As a result, these sorts of displacement systems are pretty hard to install and maintain. A lot of times they don't work well at high frequencies, and they can be pretty expensive, right? So what about velocity? Can we measure that directly? Well, the answer is yes. You can deploy a piezoelectric, a geophone. There are some LVT technologies that are basically a suspended magnet and coil together that can be deployed to monitor velocity directly and produce a signal that can correlate to that velocity. The problem in general with velocity-specific sensors in the IoT setting is that they're expensive and they typically are hard to miniaturize. So when we're talking about an IoT device, both of those things are kind of a non-starter. So where the field has really gone, and where we at Grace has gone, is to develop technologies built around monitoring acceleration. And that can be done in a variety of different ways, but we're typically using either a microelectrical mechanical system or a piezoelectric accelerometer to measure that. And those can both be miniaturized and put in a nice small chipset or a module like the one you see here. They're relatively inexpensive. You can buy a pretty nice accelerometer for less than $100 in a lot of cases, and that device can be actually used to create not only acceleration data, but it can be numerically converted into velocity or displacement. We just do a numerical integration after the fact. We can take that data and convert it into these other metrics. So to kind of summarize what happens, right? When we're monitoring vibration. First and foremost, we need a defect that's going to cause the thing that we're monitoring to move, in this case, that bearing, right? That accelerometer that we placed, in this case, on top of it is going to create that vibration that it's seeing. In this case, acceleration, it's going to convert it to a voltage. So you're going to see a voltage output that's either going to be single axis. In this case, you've got two axes of acceleration happening at the same time, both horizontally and vertically. We're going to take that data and put it into what they call an analog to digital converter. So that's taking that voltage data and it's going to convert it into a set of numbers that will range between a 0 and some high end. That's going to give the computer the ability to look at that sine wave that you see and process that down. And then from there, some sort of processor is going to come in, analyze that data, and display some sort of data to the user, some sort of processed information, and issue alerts from there. So I'll get into all the details of that, but pretty much anytime we deploy an IoT-based system to monitor vibration, this is the process that's occurring. So once we've kind of got that monitoring system in place, what do we look at, right? I'm going to pose a couple of questions here and then answer them as a way to get into those details. So the first question is, does amplitude matter? Does the amount that this thing is moving, does it matter? And the answer to that is absolutely yes. It does matter the degree of amplitude, the degree of movement that we're seeing in this particular object. And that's pretty intuitive, right? The more you see something vibrate, the more we would expect it to be degrading, right? And I kind of say this here in a more elegant way. Bigger defects tend to lead to larger vibration amplitudes, right? So if I've got a clean shaft that's not affected by any sort of defect, I get an amplitude like you see here, a green amplitude. If I add some sort of defect to that, I'm going to start to see a larger amplitude coming out of that accelerometer. And if that defect grows, we're going to see an increase in the recorded vibration, right? So that's pretty much true universally. If you see more and increasing amplitudes, that's a bad thing. But there's a caveat. There's a huge caveat to this because the severity of the damage that you're seeing from that amplitude is heavily dependent on frequency. So I want to kind of cover that in a couple different slides here. And really the idea is to just use graphics to convey these concepts. So in this case, I've got two bearings and I'm going to subject them to an identical displacement, but at different frequencies. Okay. So the bearing on the left is at a low frequency and the bearing at the right is at a frequency that's 10 times higher than that. If you saw this in your facility, it's very clear that the one on the right is not behaving well, whereas the one on the left, depending on the circumstance, might not be subjected to as much damage. So in general, when you have a higher displacement or a high displacement, that's going to be more damaging at high frequencies. So displacement is more damaging at high frequencies. Now, if we flip that around and look at acceleration, okay, so I've got same two bearings, they're subjected to an identical acceleration at different frequencies. Again, these are frequencies that are 10 times, an order of magnitude different, right? So in this case, we've got a high frequency application on the right that seems to be, it's clearly vibrating, but it's not vibrating that much, right? On the left, we have a low frequency application with an identical acceleration, and it is vibrating a lot, right? So this is actually the opposite of what we just saw with displacement. Acceleration is actually more damaging at low frequencies, okay? So those two things are super important. And that brings us to the last kind of mechanism for evaluating vibration, and that is through a velocity measurement. So again, same exact thought experiment. I've got two bearings that are running at frequencies that are 10 times different, right? And they're both recording the same velocity, okay? And in this case, because we're looking at this from a velocity perspective, it's kind of hard to tell which of these bearings is actually undergoing the more severe defect, right? And that's because velocity is actually relatively equally damaging across frequencies. So when you see me moving forward in this presentation talking about velocity-based measurements, that's why. It's because regardless of what the shaft speed is of that particular asset or the frequency at which the defect is manifesting, if we look at velocity, those amplitudes are going to be consistent, so we can draw thresholds that are pretty universal for when vibration gets to be too much. And so this actually drives right into that. This is a chart that comes right out of the ISO standard for looking at vibration severity in rotating machines. And I'm not going to go into any detail here other than to show you that they basically just come out and they group machines in 4 different categories, and they look at a velocity measurement. So this is the peak inch per second that's experienced by that particular group and where it becomes severe. So you can see that these are pretty, rigid lines for a large machine. If you get a velocity that's over about 0.3 inches per second, it doesn't matter. It's a damaging scenario. So it allows us to view these thresholds in a more universal sense and makes vibration analysis a little bit more easy to deploy on a variety of different assets. So, second question that gets answered is, does the frequency matter? In terms of when we put an accelerometer on something, does the frequency of the output matter? And yeah, the answer to that is absolutely. Frequency is often indicative of the type of defect. So while amplitude kind of tells us about the severity of something, frequency lets us hone in on what exactly is going in within that system. So we at Grace break that into a subset of categories that are seen here. We look at subsynchronous behavior that occurs at frequencies lower than the run speed. And that typically is indicative, if we see elevated amplitudes there, of looseness or isolation and isolation issues. If we look at synchronous data right at the run speed, that can be indicative of unbalance or eccentricity, gear tooth issues, that sort of thing. Harmonic behavior that's going to occur at multiples of that run speed. That's typically indicative of alignment problems, or you got a blade that has a crack, or a gear that's chipped, a gear tooth that's chipped. These things occur at multiples of the shaft speed. We also can experience non-synchronous behavior that actually is not tied to the run speed with a targeted integer. And those are typically tied to problems with belts, electrical systems, bearings. If you've got a bearing, the geometry of that bearing will define how many times per rotation of a shaft that you see an event occur. And then when we get up to the high frequency stuff, we're typically looking at gears or bearings. So I've got an image down here at the bottom that's kind of demonstrating this. If we've got an unbalanced problem in the shaft, it's going to manifest with a sine wave that kind of picks up an issue once per cycle. Whereas if I've got a blade that's damaged, every time it spins, we're going to see in this 8-bladed example, we're going to see 8 kind of 8 cycles of that blade in one spin of the shaft. So how do we measure frequency, right? We've talked about how to measure vibration and how to kind of look at amplitude there, but how do we actually get at these frequency measurements? Well, to start with, we're going to capture that vibration using an accelerometer, just like we talked. We're going to run it through an analog to digital converter and then push it into a processor. That processor is going to take that acceleration data and convert it to velocity using numerical integration. So we talked about this before, right? Acceleration is just the change in velocity, so we can back out the velocity measurement by using numerical integration. And once we've got that time history waveform of acceleration data being expressed in velocity units, we can convert that velocity data into the frequency domain using a Fourier transform. And again, this is not a higher level math class. I'm not going to get into the details of this Fourier transform, but it can be done in a discrete way on data that we've captured using a processor to provide data in a frequency specific context. So I'm going to use some graphics to describe this. Let's say we have two different defects occurring at the same time, right? Same ones we talked about before. And as a result, we're seeing a 1 cycle per second failure occurring in this acceleration data and an 8 cycle per second defect occurring out of kind of this higher speed asset, right? The blade pass. We're going to end up with, and this is highly simplified for those of you who come at it from the application perspective, but we're going to come at it, we're going to get a signal that looks something like this when you combine those two defects together. This is what comes out of the accelerometer, okay? From there, we're going to perform that numerical integration step that I talked about before. It's going to take that acceleration data and process it down to produce a signal that is expressed in units of inches per second. So instead of looking at an acceleration, we're now looking at a velocity. It looks very similar to the naked eye, but the units have been changed appropriately. We then are going to perform a discrete Fourier transform, which is going to allow us to take that data and present it in a kind of different way, right? So this plot that you see at the bottom right hand of the screen, this is on the x-axis. We're actually looking at frequency now. So this is frequency in terms of hertz, and then the y-axis is the amplitude of the signals that are occurring at all those different frequencies. So you can see here exactly what you'd expect. There's two spikes, one at the run speed, which is indicative of this unbalance that we got going on, and then one at that blade pass frequency, which is 8 times the run speed. So again, there's a lot of kind of oversimplification I'm doing here, but generally this is the way this works. And I guarantee that you all have seen this in practice, because you've almost undoubtedly seen it on a stereo of some sort, of graphic equalizer, or just a standard, car stereo. The way that this works is that, your stereo, your audio output is broken into bands the exact same way that we just talked about here. They take that frequency spectrum and they break it up into individual kind of bands inside that frequency spectra. And you end up with the ability to take a graphic equalizer and turn up your bass, for example, in the lower frequency bands. Or, it's just displayed on your dashboard as kind of a cool looking up and down for music that may have higher frequency content, right? So we're not doing any magic here. This is very commonly used in a variety of other industries. So what we do is when we're looking at rotating equipment, instead of breaking it up into frequency kind of specific bands that are targeted at given frequencies, we actually tie those bands to different physical outputs from the rotating equipment. So I kind of mentioned these a little bit before, but at Grace, we look primarily at the 7 bands that you see here on the screen. We've got a subsynchronous band, a 1x, 2x, and 3x band. Those are multiples of the run speed. We have a bearing band, which is just kind of a catch-all for bearing behavior. And that can bleed into these other 2 bands, which are our low harmonics and our high harmonic bands. And you see at the bottom of this figure how those bands can tie to different defects in a piece of rotating equipment. So the process here really is to couple amplitude. You can see that as the height of these bars with the band in order to do an assessment of where defect or degradation might be occurring in that rotating system. So when we're looking at rotating equipment, again, the overall, we call it RMS, root mean squared, kind of level of that vibration is going to increase with time, right? In this case, I've got an example down here. We've got a bunch of activity occurring between 3.2 times and 12.2 times the run speed. And that is what we defined as our bearing band. So if I look at this plot and I see that over time, we're seeing an increase in behavior between 3.2 and 12.2 times the run speed, a lot of times that's an indicative thing of a bearing fault. Now, in this case, we've got access to all the data. This is not really your typical IoT rollout because we're not sending all this information all the time in the IoT world. But let's say you had access to this. We actually can go in here and define some narrow bands around your outer race ball pass frequency and your inner race ball pass frequency. Those are red and green, right? So when I look at this plot, I actually can see that over time. So as time progresses here up on this time axis, I actually see this increase in behavior in these very specific outer race ball pass frequency bands. And that tells me, you know what, there's an outer race issue with this particular bearing. We need to perform maintenance activities accordingly, right? So this is how frequency can be used to help hone in on a specific defect in a piece of rotating equipment. So again, to kind of recap what we've talked about so far, vibration can be used to allow us to see defects earlier than we could if you're just monitoring temperature and current, and certainly earlier than you can if you're waiting for the equipment to start making noise or something, right? We need to look at amplitude in order to get an indication of the severity of a defect, and we need to look at frequency in order to figure out the type of defect that's occurring. I also want to point out that accelerometers most times are going to be the most accessible vibration monitoring transducer. But ideally, we're actually looking at velocity, not acceleration or displacement, because that's going to allow us to look at defects as they're occurring in a way that's independent of the frequency at which those defects are propagating. Okay? All right. So with that as a very, very quick primer on what vibration is, I want to talk about how vibration monitoring works in practice. So historically, vibration monitoring has been performed by trained analysts who are going to basically walk through a facility using handheld equipment to check whether an asset, a piece of equipment, is vibrating in a way that is unhealthy, right? And these analysts are certified against some ISO standards. And then they're looking at data against those ISO vibration standards that we've looked at before. So typically these routine-based inspections or these RAP-based inspections are done monthly or quarterly. So you get a trend of degradation over time. And you can use that trend to assess whether or not maintenance activities are needed and then dig in on what exactly that maintenance activity should be. So that data, in this case, is analyzed on the spot. It's looked at for important features, usually kind of coming out of that banded amplitude, and then it's trended over time. So what I want you to take home from this is that if we could do this instead of monthly or quarterly, if we could do this every hour, that gets you a lot more information to be used to make decisions. If you got more frequent data, that's going to allow for earlier indication of faults. And a lot of times, it's going to catch a fault that actually occurs between vibration analysis cycles. So that's why we're interested in using IoT technologies in this space. So because of these advantages, we've really seen a lot of options start to emerge over the last, actually a couple of decades to provide 24/7 vibration monitoring. Rockwell actually has some really, really high-end stuff in the Dynamics series that will get you real-time 24/7 vibration monitoring of critical assets. The downside of this equipment, because it works well, it's super great, is that it's expensive. It's really designed for critical assets, things that need to be monitored all the time. And as a result, it's just too expensive for balance of plant installations. If you want to monitor, every single compressor, every single pump in your facility, this can just get out of hand from a cost perspective, both in terms of the hardware and the installation of those sorts of technologies. So when we look at IoT technology, we're looking at bringing down those costs to allow for a balance of plant type of deployment. So as a result of that demand, there's been just a slew of IoT technologies in the last really 5 years that have emerged that have revolutionized the ability to monitor vibration in the industrial setting. Typically, what you're seeing in any of these platforms is a low-cost suite of sensors that are integrated within some low-cost hardware and a relatively low-cost entry web-based software. So you purchase the web-based software that gives you access to this data that's being captured by this low-cost hardware. And we couple that with battery-powered wireless communications and easy installation to provide, a system this really, could be deployed on pretty much any motor in a plant to give real-time data, or at least once an hour, every 4 hours, whatever the number is, information coming from your rotating assets, right? This is why IoT-based vibration monitoring has been so, or at least has the potential to be so impactful. So, with that, again, as a background on what's kind of going on currently, let's dive into what 24/7 IoT-based monitoring would look like in an industrial facility. And the way I'm going to tackle this is instead of trying to do this in my typical PowerPoint-driven way, I'm actually just going to look at 7 questions that we get pretty frequently about concerns or just general questions about how an IoT-based vibration monitoring system would work. And hopefully that'll convey the breadth and depth and scope of what an IoT-based 24/7 monitoring system would look like. So the first question that we get a lot is just generically, do wireless accelerometers work? Second question, is the accelerometer bandwidth sufficient in an IoT system? Thirdly, how important is doing onboard analysis? Can I effectively use an IoT technology to monitor bearings? How much early warning can this IoT system give me? I can't use the cloud in my application. Can I get this data into a PLC? And then lastly, can I monitor other stuff that's not vibrating? So I'll touch on each of these one at a time in kind of some separate slides. So the first question is, do wireless accelerometers work? And wireless is key here in the context of an IoT deployment, because almost all industrial Internet of Things based vibration monitoring solutions are going to have a wireless component. So the benefit of doing a traditional wired install is that communication is reliable. It's coming through all the time, no questions asked. You have nearly unlimited bandwidth because you can send as much data as you want back to that computer that's doing your processing. And everything's wall powered, so you don't have to worry about running out of power. Like, again, this high-end case, these are the reasons for it. But as we've talked about a couple slides ago, it's expensive to install a wired system. Sensors are expensive generally. Cable and conduit, that's expensive. Labor to do it's expensive. And, honestly, sometimes it's just infeasible to deploy a wired vibration monitoring system in a given application. So as a result, IoT has kind of come along with these wireless accelerometers. They're inexpensive to install, right? The sensor's inexpensive, and a lot of times it's just a magnet. You just plop it right down on your asset and you're done. That comes with some drawbacks. With any wireless thing, you're going to get less reliable communication. I won't sugarcoat that. If you got a fork truck that comes and parks in the way of your sensor, it's going to degrade its ability to transmit its data. There's going to be limited bandwidth. So depending on how the system's played out, you got a bunch of these. They're all going to be using that same wireless bandwidth, and it is limited. And most of the time, these wireless accelerometers are battery powered, which means you got to change batteries. And that is a downside to an IoT-based system. So, the answer to this question, do wireless accelerometers work? Well, sure. The question is just, how do we overcome these concerns that wireless communication isn't reliable all the time, bandwidth is limited, and devices are powered by batteries? I'm going to restate these as 3 concerns. I can't constantly monitor vibration for machine protection because the wireless communication is down. I can't constantly send raw acceleration data because I don't have enough bandwidth, or I need to periodically change batteries because these wireless devices require battery power. So I'll address each of these concerns one at a time. The first concern, I can't catch brittle failure because I can't monitor equipment 24/7. My response to that's true. IoT systems that are wireless and battery powered are not ideal for cases where you need to see that wrench that fell in the system. So limited wireless bandwidth and limited battery means that all of our sensing and processing and communication is done in bursts. So these nodes wake up for, say, 1 second every hour and then send their data. So if an application actually demands a system that can immediately respond to a vibration event, I really think, you should use a higher end system. The take home here is that these IoT-based systems are really designed to capture and quantify degradation that is progressing slowly over long periods of time. So, the bearing generates a defect and it's getting worse, and you need to, within the next month, replace that bearing. That's the kind of thing we're targeting. So the second concern is that wireless sensors can't provide raw data. They can only provide process data. Well, that is not a valid concern. It's true that most wireless IoT-based vibration monitoring systems can't continuously stream raw acceleration data because of the battery and bandwidth restrictions we just talked about. But they can internally process that data down and then provide process results fairly regularly. So in our system, what we do is we process that down and we provide that banded frequency analysis once per hour. So the amount of data that we're sending, it's really like 65 data points per hour, 130 bytes per hour. So the other thing, a lot of wireless accelerometers can actually provide raw data occasionally. So if you really want to dig into that raw acceleration signal, you can ask for it. It's just, we can't do it on a regular basis because it'll degrade the battery and consume all that wireless bandwidth. So the last question is, or concern, excuse me, is that changing batteries in one of these devices is a pain. That is true. I mean, without a doubt, anytime you got to change a battery, it's a pain. That, however, is not always an issue. Most of these systems that are available today have battery lives that are at least a year. So you hopefully are not changing batteries, more than once a year. If not once every 5 years, with an hourly data collection. The other thing, some accelerometers, some of these wireless systems can be powered using an outside 24-volt source. So that eliminates the battery power problem entirely. And the last thing that I'll put out there is that I think energy harvesting technologies are coming along that are going to allow these wireless accelerometers to be perpetually self-powered. All right, so second question, is accelerometer bandwidth sufficient? So when I talk about bandwidth here, I'm actually not talking about frequency bandwidth. I'm talking about the bandwidth of the accelerometer. So this is when you go to buy any accelerometer, it's going to have a maximum frequency that you can monitor. And a lot of these lower end MEMS or piezoelectric accelerometers just don't have the full bandwidth that you'd expect from one of these really high end systems. So it is true, absolutely, a lot of these accelerometers can't resolve those high frequency signals. But I think a low frequency device can still provide an early indication of failure in most applications. They do have a hard time with gearbox or fluting problems, and definitely a higher frequency device that has a higher bandwidth can provide earlier indication in a lot of applications, bearing applications being one of them. But you can get a lot of benefit out of one of these low-end devices, to be quite frank. Secondly, a lot of IoT offerings actually have come with a relatively high bandwidth accelerometer, up to maybe 5 kilohertz. And these give a pretty good resolution on problems occurring, in that bearing or gearbox world. I will say that, one thing that can happen here in an IoT system that can bring in other types of sensors, well, you can couple your vibration sensing capabilities with an ultrasonic transducer and get a kind of coupled system that gives you the best of both worlds. So here's an example in our world. This is our low-cost VBT1. We have a device that is low cost and 800 hertz. And then we have a slightly higher end device. We call it our VBT2 that gives you a higher accelerometer bandwidth. Now, in our world, we also can pull in an ultrasonic sensor to one of our panel mount devices. In this case, we've got just a standard 4 to 20 milliamp ultrasonic sensor that can be deployed on the same asset, and we can bring all that data together in our cloud and give kind of the early indication from the ultrasonic sensor and all of the analysis that can come out of the lower end or lower frequency vibration and temperature offerings that you see on the left. All right, third question. How important is it that our IoT device has an onboard or banded analysis capability? Because some of them don't. Some of them just provide a overall level of amplitude. So none of that banded stuff we talked about earlier. And my answer to that is it really depends on what you're trying to do. So there are low-cost systems that can provide you just RMS vibration. And that RMS vibration in a lot of cases is sufficient to let you identify the onset of anomalous behavior and then track its severity over time. What it's not going to let you do is classify what's happening, right? So you know something's happening in that rotating asset, but you don't know exactly what it is. So again, the example here comes out of what we talked about earlier. If we don't have this suite of information, there's no way in my example that I'd be able to point at the fact that this was an outer rates defect. If I didn't have any of that analysis, I would definitely know something's going on, but I wouldn't know what it was. All right, the fourth question here, and we get this a lot. Can I effectively monitor bearings using an IoT system? And my answer to that is yes. Many bearing issues can actually be seen just by using an overall RMS value from an accelerometer, that's got a bandwidth equal to or greater than 800 hertz. So this is a relatively low-end entry to the IoT space would fall there. If you look at this, these plots on the left, this is actually the results of an experiment where we ran a bearing to failure. And this black line that you're seeing at the very top, this is just our overall RMS level of vibration. You can very much see here that, hey, something happened. We see a massive increase in our overall vibration levels. And, that's what you'd get from a vibration sensor with an 800 hertz threshold. Now, if you have a system with a bandwidth that's greater than about 2 kilohertz, and you've got a banded analysis capability as well, this will allow you to know that for sure bearings are at fault. So again, if you look at these plots on the left, the red line, the pink line, and this the light blue and the dark blue line, these are all low frequency bands. So the dark blue line here is our subsynchronous band. The red line is our 1x band, and then the pink and light blue lines are our 2x and 3x harmonic bands, right? So you can see in this case, this is not happening at the low frequency. It's happening at a high frequency. And so if we bounce down to this lower plot, these are looking at the bearing band, which is this kind of bluish band that's got dotted lines. We're looking at the red line here, which is our low harmonic band, and we're looking at the pink line, which is our high harmonic band. So again, if you've got this banded analysis in place, you can look at these signals down here and really see, okay, yeah, there is a bearing issue that's occurring, and you can kind of track this blue line as it gets worse over time. So, yes, we can effectively monitor bearings with an IoT-based system. And even, at the best case, a super high-end vibration system in the IoT world will allow you to get potentially remaining useful life predictions using these sorts of banded analysis. So absolutely, bearings are a target that we can target with IoT-based systems. All right, fifth question we get all the time. How much early warning can I get by deploying one of these systems? Well, that really, really depends. I can't answer that. But rule of thumb, if you're looking at just RMS-based vibration amplitude, you typically can get hours or days of early warning that something's happening. If you layer a banded analysis on top of that, that can actually extend out. You can get, up to a couple of weeks worth of early indication that you have a problem. And then if you layer predictive analysis on top of that, really depends, but let's say you could get up to a month of kind of early indication that something is going wrong and something should be replaced. This plot at the bottom is kind of an example of this. We have a customer that cleans their fan that we're monitoring here once a month. And you can really see it. In this case, it's not really degradation. It's just that fan is getting gunked up and then they clean it. This is the sort of indication you get. So these cleaning points happen, once a month, and then near the end of that month, that thing starts to creep up. Well, if this was truly an issue, you would start to see it pretty quickly after these trends start to elevate, right? So this is just an example of what that data might look like from an IoT-based system. Question 6. I can't use the cloud in my facility. I have some restrictions, IT or otherwise, on getting data out of the building. I would really rather get this data into a PLC. So can I do it? Right? And then my response to that is actually yes, but it's going to be super heavily dependent on the system. We go into a lot more detail on this in a lot of our other presentations, but here's the gist. In a standard IoT system that you get from pretty much any vendor, you've got some sensors, they send data to a gateway, that gateway sends data up to the cloud, and then that cloud data is made available to a suite of either web or mobile applications, right? That's your IoT-based system. On the other side, your control environment is very limited. You have typically wired sensors that are sending data directly to, a PLC or SCADA, and that data is being made available via an HMI. So these are two very different worlds. There's a variety of different ways in which these can connect, though, and that's what I want to drive home here. If we have an IoT-based vibration monitoring system, I can get data into that PLC using a cloud-based RESTful API. Not all PLCs are compatible with this, but some are. This is kind of option number 1. Option number 2, we can use a broker, either MQTT or OPC-UA. This broker works by taking data from our gateway and making it available both to the cloud and to the PLC. Again, you need a PLC that's got kind of some higher end or more recent technology so that you can build it to get into that broker, or you need to build some sort of interface software on the plant side. And the third option is to actually bridge that gap using an industrial protocol like Ethernet IP. Our devices allow for either Ethernet IP or Modbus TCP/IP communication from gateway to control system, and they actually will provide both a control gateway as well as a cloud gateway at the same time, so you can kind of get the best of both worlds. So the answer here is yeah. I know the Internet of Things kind of hinges on a cloud, but in the industrial setting, sometimes that's not an option. So yes, absolutely. The answer is, at least with our system, you can use your standard control focused technology to get data out of these vibration sensors and use it effectively. All right. So I think this is the last of the 7 questions that we get frequently. Let's say you've deployed a number of vibrating sensors or vibration sensors, and now all of a sudden you say, well, we actually have some other critical assets that require monitoring a fluid level or a pressure differential or a current draw. Can I monitor those other things? And the answer to that is absolutely yes, but it really depends on the system. So again, I'll talk about the Grace stuff here because it's what I know. We have a panel mount device that is heavily configurable. So you can come in and you can say, I want to pick up some thermocouples and a 4 to 20 milliamp ultrasonic sensor like we talked about earlier. Well, it's pretty easy for us to spin this device up, collect that data and start providing that to you either via the PLC or the cloud, in right alongside your vibration data that you've been capturing. So yes, absolutely. In a system dependent way, we can, deliver other data that's not vibration related using kind of a vibration focused IoT system. So, to wrap this all up, I just want to reiterate, vibration monitoring is a really powerful tool for reducing unexpected downtime, for minimizing maintenance costs in the industrial world, and for increasing worker safety. I want to reiterate that route-based inspection. So if you're using a standard route-based approach to vibration monitoring, it's really only as good as the frequency of that inspection. And, the quality of the inspector, right? But the frequency of the inspection is what drives the demand for an always-on 24/7 IoT-based vibration monitoring system. So I also want to, the kind of take-home message here is really that IoT technologies are ready right now to bridge the gap between that vibration inspection world and 24/7 vibration monitoring. And in many, not all, I mentioned at the beginning, there's a lot out of scope of what I talked about here today, but many applications in the industrial setting. So with this, I want to close. I want to thank you all for sticking with me for almost an hour here. If you have any questions, please feel free to reach out to me or our sales team at Grace. We'd love to get a discussion going with our application engineering team or our customer success team, and get you set on your way towards, a successful deployment of 24/7 IoT-based vibration monitoring technologies. So, thanks again. We'll talk to you soon.